talk about this. Here we talked about this in an earlier slide, but if we have a position versus time graph that looks like a parabola, that means if you take the derivative of that, you get a straight line because this is a squared value. This is a linear value, okay? But then if we have this line that's sloped and we know we can take another derivative to get acceleration, what does our acceleration look like for this?
Horizontal.
Should be a horizontal line, okay? Which you would call constant acceleration. And in this case, this would be called average acceleration if you just take the slope of the line. Because remember, average acceleration is change in velocity over change in time, but the full definition of acceleration is the derivative of velocity with respect to time, or the second derivative of position with respect to time. Yes?
Like instantaneous.
Instantaneous, yes. So here that is spelled out, right? Here is our definition of acceleration. The instantaneous acceleration, like you said, is defined as the derivative of velocity with respect to time. Also, the second derivative of position with respect to time, okay? And just to give you a sense of where we're going, in chapter 5, we start talking a lot about forces, okay? So we're getting there. We're on chapter 2, and then I think actually in chapter 4, we also talk about forces. But when we're talking about forces, it turns out force is proportional to acceleration. And if you've seen some of these Newton laws formulas before, you know what the constant is that we're dealing with because we have F equals ma. But the key here is anytime you see an acceleration, there's a force, okay? Velocity doesn't necessarily mean there's a force. And a change in position doesn't necessarily mean there's a force, but an acceleration means there's always a force, okay? So basically, things don't move without a force, but they can keep moving if they're already moving without a force. It's a subtle difference. Okay, things don't start or stop moving or speed up or slow down without a force, right? Or change direction. But if they're moving already in a straight line at a constant speed, they can keep doing that. And if they're stopped, they can keep doing that. Okay? So, but what I'm saying in a lot of extra words is force is always related to acceleration. And acceleration is changing speed or changing direction. All right? Actually, I will put it in the slides, but I actually found a really fun physics meme about that the other day. So we'll put it in. I'm very excited about it. You too can be excited about it. So anyway, if you wanted to figure out the acceleration from this is acceleration constant. If we have constant acceleration, that means our velocity has a constant slope, right? So if we go backwards, we know if we have something that looks like this, right? If we start from acceleration, we have something that looks like this, the velocity should look like this. What would the position look like? Like a parabola, okay? We also know if we have constant velocity, then our position looks like this. So if we have a parabola, then we get a line, then we get a flat thing, okay? If we have a flat thing, we could go back to line to parabola. So this is important. This comes up a lot because what thing has constant acceleration that we deal with all the time? Gravity, okay? So we often see parabolas in motion. Basically, anytime you throw or launch something in the air, you see a parabola. It's very pretty. That's nice that we have such a nice gravity that gives us nice parabolas, okay? There's also a very big side note. In the history of college football in the U.S., it used to be a lot more like rugby, so there was no forward passing. But then a lot of people kept dying, which wasn't cool. So Teddy Roosevelt and the Carlisle Indian School, which was that's a whole different backstory of dark American history. But have you guys heard of Pop Warner? He was the coach for that school. So they played Harvard and Yale, and I'm sure when you think of college football, you think, Harvard and Yale. But most of the rules of college football that are different from rugby were invented by the Carlisle Indian School and Pop Warner to be able to compete with these other schools. So anyway, people kept getting killed, and Teddy Roosevelt and everybody got together and we'll change the rules so they're not just smashing each other a lot. And that's how the forward pass was invented, and it's a beautiful parabola. Bringing this back to physics, okay? Parabolas, very important historically. Okay, so if you're interested in any of that story, there's a really good book called The Real All-Americans that talks about the origins of college football. And kind of a fascinating / depressing read. And it includes like Teddy Roosevelt and Jim Thorpe. And if you don't know who Jim Thorpe is, he has a really good drunk history episode about, he's like the most athletic man of all times. And he won like all of the Olympics, but was still really poor. So anyway, life is unfair. And constant acceleration, an object's acceleration is uniform. Remember, uniform just means what? Constant, right? Doesn't change. If its velocity versus time graph is a straight line. Okay, so that's just saying something in calculus. Okay, we're going to do this example. It doesn't require a lot of writing. So let's say a bicyclist has a velocity of 10 meters per second and a constant acceleration of 2 meters per second, which is just meters per second squared, but we're being silly. So what's her velocity 1 second later? 12. How about 2 seconds later? Yeah, so that means we're speeding up by 2 meters per second every second. That's all that means, okay? So here's a long thing that just says that, all right, if you like reading instead of hearing. Lots of different learning styles. All right, then I want you guys to try this one out. Let's say you're going negative 10 meters per second, and you have a constant acceleration, the same constant acceleration of 2 meters per second, but it's positive. What's your velocity 1 second later? -8. How about 2 seconds later? -6, okay? So, because we now have initial negative velocity and a positive acceleration, what does this mean? What would you call this in regular life? It's slowing down, or deceleration. But remember, the only difference between speeding down and slowing up is whether your initial velocity and your acceleration are lined up or not. Okay? So if they're both positive, then you're accelerating. If they're both negative, then you're accelerating. But if one is positive and one is negative, then you're slowing down. Okay? So both positive, speeding up. Both negative, speeding up, but in a different direction. Opposite, then you're slowing down. Okay? Doesn't matter if the velocity is positive and the acceleration is negative, or the acceleration is positive and the velocity is negative. If they're opposite, then you're slowing down. Okay? So here's a question about that. There are answers? Ooh, we are not going to do this one again. It is B. I explained that well, I guess. So the car is traveling eastward and slowing down. Let's say it's traveling this way. That means the acceleration has to be the opposite direction in order for it to be slowing down. What would happen if the acceleration was this way? You'd be speeding up. All right, you guys are killing it today. This is what you get when you get an hour off. Okay, so representing acceleration, okay? Almost all cars can get to 60 miles per hour, but what makes a good engine much different from a bad engine? How fast you can get to 60 miles an hour, and that is talking about acceleration, right? Because the engine has a certain revolutions per second, and it can speed up quickly, and that's going to be the important thing about if you're driving this car versus this car, how fast can you speed up? All right. So if we want to plot these like we've been plotting things, let's say here's our Corvette, and this is the stair car. Okay, you can tell what's different about these two things. The slope, right? Both of these are constant accelerations, but which one has a much better constant acceleration? The Corvette, right? And honestly, it's probably even more dramatic than this, but let's say this one's 5 meters per second squared, and this one is 2 meters per second squared, okay? So if you plotted these as an acceleration versus time graph, it would look like this. So they're both constant accelerations, but this is a much better one, assuming you want to go fast. Maybe you like driving a car that stairs. I don't know. Anyway, we just talked about this. Signs of acceleration, speeding up to the right, slowing down to the left. This is what things look like. Okay, we're not going to, I think you guys get this general idea. So let's try another clicker question. Sorry guys, for some reason this hour is just all questions. All just you demonstrating what you learned. All right, we're not sure, but at least we only picked A, B, and C, so that's neat. Okay, please discuss and we'll vote again. Ooh, it's better. So we'll go through these. The first one, if a car is traveling eastward, its acceleration is eastward.
No, that's not.
No, that's only true if it's speeding up. If it can have an acceleration westward, and then what would happen? It would slow down, okay? So A is false. B, if a car is slowing down, its acceleration must be negative. Not quite, right? Because a car could be going in the negative direction and have positive acceleration, or, there's lots of different options. It's not that it's negative, it's just that it's a different sign from the velocity. So the answer is probably C, just because we know that it's not A or B. Hang on. But let's talk about this. This is a little bit crazy, and I want you to pay attention to this. A particle or anything, a car, with constant acceleration can never stop and stay stopped. What does that mean? It means, like, even if you have a zero velocity, it's a turning point, right? So when I throw this, the only time it has constant acceleration is when I'm not touching it, right? When I'm holding it, what's the acceleration? 0. But as soon as I let go of it, what's the acceleration? Negative 9.8, right? So it slows down and it comes to a stop, but does it stay stopped? No, it has to turn around and start accelerating down. And unless it hits something, it just keeps accelerating. So if you're out in space, right, it would keep going. Yes? Well, then the acceleration changes when you hit the wall, right? That is a constant acceleration from the perspective of the car, but as soon as you impact the wall, so we'll get into this, but acceleration is the sum of all your forces divided by mass, okay? So there's a force from the wall. So once you start adding in extra forces, you change the acceleration, because the acceleration comes from the net force. Yes?
Wouldn't 0 also be constant because it's consistently 0?
Oh. Good job. So yes, if your constant acceleration is 0, there is a slight caveat to this. It's tricky because the word stop sort of means that it was moving at some point, but that is a slight loophole to this answer. So good job. Like I said, not the best question. All right. So signs of acceleration, this is basically what we're saying. You can speed up to the right, slow down to the left, slow down to... So all the signs, doesn't matter if it's positive or negative. What matters really is the slope and the relative signs of the velocity and the acceleration. Okay, so all that matters is the slope and the relative signs. And how much time do we have left? Okay, I'm just going to do one more slide. So just vote on this one really quick. We can always continue this next time. Oh boy. Okay. So let's look at this in sections. Wherever our acceleration is 0, our velocity should be constant and therefore flat. So what I mean is here and here, our velocity should be horizontal. So basically flat. So that's here and here, here and here. That doesn't narrow it down a lot. All of these are pretty much constant velocity there. Then we have to consider this piece. So this piece is a negative acceleration, which means that you're going to have a slope that goes down. So that actually covers all 3 of these, but not this one, because that one doesn't have, that one has a 0 velocity, which is not what's going on. And so in order to figure out which one is the correct one, you actually have to read the question. And when you read the question, you'll find that what it says is the particle is initially moving to the right and eventually moving to the left, which means that the particle changes direction. And in physics, what changes direction means is that we have to cross 0. It means we have to have at least an instantaneous velocity of 0 whenever we're changing direction. So the only graph that shows that is this. These are all the same shape, but that means that B is our correct answer.